Okay, let's get started. So we were looking into the dynamic Smagorinsky model. So we learned about test filtering, and we also understood the concept of dynamic Leonard stresses, which is essentially the Lij was equal to Tij minus, so this Tij SGS at the test filter level minus tau ij SGS test filtered. This is equal to ui filtered, uj filtered, both at the grid and the test level, minus ui bar, uj bar, sorry, this is whole test filtering, and we learned that this is exact now. This entire part is exact. We have access to this because the ui bar is the grid filtered velocity that you are calculating in LES, and on the test filter level you can do one filtering operation. Okay, so this is the test filter level SGS, this is the grid filter level SGS. So essentially what we are doing is, in a Smagorinsky model we want to compute, if you recall, in Smagorinsky the length scale is the subgrid length scale, right? So this LSGS, let's call it, this was essentially CS delta, right? So to compute new SGS, I am using this length scale square followed by a time scale, inverse time scale, which was the square root of 2 Sij filtered. So the LSGS is the subgrid scale contribution, or the subgrid scale AD. Obviously has to be smaller than the delta. That means CS has to be less than 1, right? It has to be a fraction, right? So since this is subgrid, this is the subgrid contribution, subgrid scale or an AD, right? So therefore CS is less than 1, and we saw that the values were like 0.25 or 0.01 or whatever, right? So a fraction value, and this is what we want to compute. Instead of fixing in dynamic Smagorinsky, we want to compute CS, right? So to do that, what we did is, let's say we took a mesh, not a mesh, let's say this is the grid filter level, okay, this is the grid filter level. So in finite volume method, implicit filtering, this is where you are actually calculating your data, right? You are computing data on these cells where mesh size is same as filter size. So I have access to this. So let's say here this is, let's say there is a subgrid scale AD here, and the contribution of this subgrid scale AD is what you want to compute in LES using dynamic Smagorinsky model, and I don't know that, and to do this I want CS delta, right, to compute the new SGS. So the new SGS was your CS delta square, right, the L square, followed by the inverse time scale, right. So this was your meter square, this is 1 over second. So this is the subgrid scale AD contribution that I want to find out, and since I have a mesh like this, let's say I have resolved, let's say I have this particular green AD, let's say is captured using this mesh at the grid filter level. So the idea of this dynamic Smagorinsky is that, okay, I have access to an eddy which is being captured at the grid filter level. I can make it a subgrid eddy at the test filter level, right? That is the idea. So what we just did is we just said, okay, so we make a test filtering operation, that is after calculating at the grid level, I make a test filter, right? So this is our test filter. Here, this particular eddy that we had, this now becomes subgrid, right? So this is resolved here, resolved using the grid filter, and this is your subgrid. Now this becomes subgrid here, but I know the exact data on the grid filter because you are computing your LES on a particular grid filter. I am just taking a test filter which is twice that of grid filter, so that I know what it is. From this I can estimate, suppose if I am going, if I am going to change the mesh or resolve it further, what should be the subgrid contribution by going one level up, right? We are not going, let us say, one level down. That you can do it in LES convergent tests. You can reduce the mesh, instead of this 4 by 4 you can do 8 by 8 or 12 by 12 so on. But at any grid filter level, I am going one level up to find out what is the SGS contribution, and using this I estimate the CS. Okay, you have a question? No. Okay. So using that information, so we said this dynamic Leonard stresses, right? So this was our dynamic Leonard stresses, which luckily is exact. I have access to the filtered velocity. I make one test filtering operation and find out the Lij. No modeling required here. So the objective now is to find out CS dynamically. For that, what we do is first we use the Smagorinsky idea also for the test filter level. Okay. So now recall the tau ij SGS model. Okay, this is tau ij SGS model is essentially you are saying it's minus 2 CS square delta square, that is your length scale, subgrid length scale, the inverse time scale, and of course the strain rate, filtered strain rate, right? So this is your new SGS in a Smagorinsky model. So I am recalling here Smagorinsky. And then followed by, of course, you have plus 1/3 tau kk delta ij. I am not using the idea that is suggested by Pope, where you take 2/3 k SGS. That requires k SGS to be computed using a, let us say, one equation model. Instead, we go back to the original equation where tau kk is introduced. So this is, I have an equation here, let us call it 1. This is at the grid filter level, right? Tau ij SGS. I am using the same concept now also for the test filter level, right? So assume Smagorinsky model also for Tij SGS, that is the test filter level, right? So what we do is Tij SGS modeling analogous to the tau ij SGS here. Of course, this is minus 2, we can call it CS square, let it be there. for some time, we don't know what it is, and then now it's a test filter size will come, square of that, okay, CS delta cap square, followed by test filtered inverse time scale here on the strain rates, Sij grid filtered, test filtered. Of course, the other part, which is 1/3 TKK delta Ij. Let's call it equation 2 here. Okay, or we call it, let's say 2 and 3. That's better. This is 2 and this is 3. Call this 1. Right. So now we would like to, of course, here where this S test filtering is nothing but square root of 2 Sij grid filtered, test filtered, and Sij test filtering is nothing but your half of dou ui by dou xj plus dou uj by dou xi, grid filtering, test filtering. Okay. So now I can use this equation 2 and 3 in 1. I can substitute to find out, I have exact data Lij, but the objective is to find CS, and CS is appearing in equation 2 and 3, and therefore I would like to substitute 2 and 3 in 1 to find the nature of the constant CS. Okay. So using 2, 3 in 1, I get this Lij is equal to, I have the first part is of course Tij SGS, right. So Tij SGS I am substituting here, so which is minus 2 CS square delta square plus 1/3 TKK delta Ij, and then this is the Tij SGS, and I have tau Ij SGS test field and then test filtering operation on that. So tau Ij SGS is, this is minus of that, so it's minus of tau Ij SGS, which is minus 2 CS square delta square Sij over bar plus 1/3 tau Kk delta Ij, and then there is a test filtering operation on the entire part. This is tau Ij SGS. Now let me just rearrange it here. Here I would like to call this CS square as simply C, because that is the dynamic constant or coefficient we would like to compute. Okay. So here let's call this, let C be equal to CS square, your dynamic coefficient that you want to find out. Dynamic coefficient. So I can rearrange it, Lij minus 1/3 TKK delta Ij, and then this is minus of minus, so this is minus but it becomes plus on this side, so I get plus 1/3 tau Kk test filtered delta Ij equal to the remaining two terms here, which is minus 2 C, C square is replaced by C simply, and that is the common in both. So I have minus 2c, I have delta cap square. Okay, I have missed this one here, and then the remaining term minus 2c of this particular term, and then here this is plus, so if I take it out it becomes minus, so I get minus delta square s Sij over bar, and a test filtering operation on this particular thing. This is the test filtering operation here. I have simply rearranged all the terms. Okay, so now I can set this particular term in the square bracket as Mij, this thing. So this particular thing I would like to call it as Mij. So I can rewrite this as essentially Lij minus 1/3 delta Ij of, so I have Tkk minus tau kk test filtered, which is equal to minus 2c Mij. So notice this Tkk minus tau kk test filtering. Let's go to equation 1. What is Tkk SGS minus tau kk test filtering? Lkk, right? So I can rewrite this as Lij minus 1/3 delta Ij Lkk, okay, equal to minus 2c Mij. If I rewrite this to get C, the objective was only to get the equation C, right? So I can get C is equal to now minus of Lij minus Lkk, or sorry, 1/3 Lkk delta Ij minus of this divided by 2 Mij. So if you look closely now, Lij is exact, right? Equation 1, this particular part here. So on any grid level, I have access to resolved velocity. I do one test filtering operation to get Lij. Okay, so this you have to do it at every time step. Dynamically at runtime you have to calculate this coefficient C, right? So this is essentially a Smagorinsky model where C is computed every time step, and to do that I pause every time step to compute this dynamic Leonard stresses. Okay, get Lij. Once I get Lij, then I have to get the Mij part here. The Mij is essentially, you know your test filter size, you know the grid filter size, and you have strain rates at the grid level. You use that to make one test filtering operation. You get Mij, then you get your C at every time step. But is C now constant, or is it a function of time or a function of 3-dimensional space? It is a function of 3-dimensional space and time, right? So this particular equation now here, so here C is now a function of 3-dimensional space and time, your dynamic model coefficient. Runtime you have to calculate this. So but later and what you generally see is not this equation. There was a slight change done by Lilly. He introduced a slight variation of this formula. So this is the dynamic Smagorinsky suggested by Yarmano et al. So later Lilly suggested 1992 suggested C be equal to set as minus Lij by 2 Mij was there. So basically that 1/3 Lkk delta Ij was dropped. Instead Mij is introduced on both sides, both the numerator and denominator, by dropping that 1/3 Lkk delta Ij, compared to if you go back and see here, minus Lij is retained, 2 Mij is retained, this 1/3 Lkk delta Ij dropped, instead it is multiplied and divided by Mij. Okay. Even then, even after doing this, there is an issue. Since it is a function of 3D space and time, the value fluctuates wildly, causing numerical convergence issue. Okay. So this is the popular version that you will see in commercial codes or open source codes. When I say using dynamic Smagorinsky model, where Smagorinsky equation is used, and to compute SGS viscosity, C is computed dynamically at runtime. Okay. So the disadvantage here compared to the Smagorinsky model is that one disadvantage here is that the dynamic coefficient that is C fluctuates wildly in space and time, in x, y, z, t. So that means this is causing numerical stability. Because essentially the C is controlling your subgrid scale length, right? Cs or the C delta, and assume that if C becomes negative, right, for some reason, then your length scale is becoming negative, the subgrid scale, causing stability issues. So you must make sure that the new SGS stays positive, or in the original equation, if you recollect, it's nu plus nu SGS together. The total viscosity is nu, the kinematic viscosity, plus nu SGS was there. So the total viscosity must stay positive in the equation, and for nu SGS to become positive, the C should not take any negative value. So that happens if you don't do any other let's say a correction here. If you just use this, it can happen, because you are essentially computing at runtime. If you have 1 million mesh, you have C at all this 1 million grid points at that particular time, and then it changes every time, right? So one way out is to actually use like volume averaging, okay, smoothing this parameter. So solution one is actually average this C along, let's say if you are fortunate to have a homogeneous direction, let's say in a turbulent channel flow, plane coed flow, or in a pipe flow, you have homogeneous direction, like along the flow direction, axial direction, or even in the azimuthal direction in a pipe, or the spanwise direction in a channel. Homogeneous direction, you can average the C. So the C, instead of becoming a 3D at a particular time step, it becomes either a planar data or a line data. So some volume averaging is done. So you can average C okay, along homogeneous direction, if you have them, of course. Okay, for example, channel flow, right? A channel flow, then upon averaging, the C is now then just a function of your wall normal direction and T instead of, so the X and Z are the homogeneous directions. So this helps by averaging. But what do you do in industrial flows where you don't have such luxury of homogeneous direction? So you can, yeah, so you can locally average them. Locally around them, you choose certain mesh around it, right? Maybe 5 by 5, 10 by 10 or whatever. Locally you can average it out to smoothen it. Okay, so you do this along the homogeneous direction or average or locally average, right? Or locally average C in industrial or complex problems. So this helps. This is one of the solutions. The other solution is, of course, you can come up with some kind of a limiter to make sure that the mu SGS stays positive. Okay, so we enforce a limiter for C so that nu plus nu SGS stays positive, that is stays positive. All right, this is clear. So this completes dynamic Smagorinsky model, exactly like Smagorinsky, except C is computed using this formulation where Lig is exact, Mig you can calculate using filtering operation of your strain rates. Okay, so now there is another class of models. So I'm as I said in the beginning of this course, I'm only introducing class of models rather than discuss every type of available model. And models in eddy viscosity can give very diverse, very different results. But in LES, it's more or less, since you are resolving most of the energy, let's say 70-80% of it, the objective of the SGS model is, or the role of SGS model is limited only to account for the SGS fluctuations. So usually regardless of the model, if you have done a very good resolution, if you have in LES, the models work well. So there are still many types of models. I am only introducing certain classes. So you had this Smagorinsky type. Now there is something called scale similarity model.